Welcome to this video lecture on data cubes. So far, you have experienced for yourself what it feels like to do data investigation using a tool such as Excel. And you have also looked at the basics of creating a data star to feed this investigation. But actually, it's just as common that the analyst will connect to a data cube rather than data star. This class explains data cubes and discusses some of the advantages they have over stars. But before we get into the detail, let us explain where cubes and stars fit into the overall structure of data warehousing. The main aim of a data warehouse is to be able to extract information from a number of different sources and feed them to an integrated data store such as a star. As data is accumulated, the volume of this star will grow over time, and that can have an effect on query performance. And so there is often a second step, which is to copy the data from the star into a specifically structured cube, and the analyst then connects directly to the cube rather than star. In the practical class that follows this video, you will do that creation of a cube. But first, let's find out what we mean by a data cube. In the opening class for this module, you filled in a worksheet about current accounts in a high street bank such as Santander or HSBC. We asked you to list 5 actions or queries that would happen every day in every branch. You then looked at how the bank's database would be used to create, read, update, or delete, in other words, to CRUD individual records within the database. What you should have identified is that the database at the transactional level is being used very, very frequently for small-scale, possibly micro-scale updates and accesses where high accuracy is of the essence. The database needs to be able to, for example, find one person's record within 1 million, update this accurately, and doing all this within fractions of a second. You can go out and buy very good relational database software such as Oracle systems that do precisely this. Then on the worksheet you looked at management level concerns. Senior management of the company are much more interested in the overview of the company. They are interested in long-term analysis, seeing how performance today compares with various periods over the past. They're interested in comparing one product line against another product line. And they are interested in how the environment, such as how their competitors are doing, affects what the company's performance is now and likely to be in the future. This means that the way the senior management want to use data is very different to the operational or transactional staff. Senior management are going to look at the data at summary level, for example, a year by year by year analysis. This, of course, involves huge scale processing, but most questions are only going to be asked occasionally. For example, once you've discovered who your biggest competitors are in an area, it's unlikely you're going to ask that same question again for at least several weeks. Arguably, management don't actually need absolute accuracy either. If they got a list of competitors and the competitor data is just a few £1,000s out, but you are comparing banks at an international scale, then detailed accuracy isn't quite as important as the trend and the relative position of things. This point is going to make quite a difference as to which data we could use for our data sources. And finally, do you notice that asking these high-level questions doesn't actually change the database itself? So the technical need to be able to write back to the database is much reduced. So there are some major differences between the needs of transactional and analytical systems. That's what we're going to explore in this module. If you've studied relational databases before, you'll be very well aware that their designs can be very complex indeed. If you enjoy giving yourself a fright, click on the link shown on the slide to see the entity relationship model behind the transactional system for the case study that you'll use in this module. If this entity relationship model is difficult for you to understand, think what it would be like to somebody who is not an IT expert. So one of the key things that we're going to do is to simplify this structure so that it directly meets the needs of whole business data analysis. We won't just be reducing the complexity of the volume of the diagram, we're also going to be able to structure the data to allow drilling from overview into more detail as necessary. So now you should be getting a clear understanding that while traditional relational databases are excellent for what they try to achieve, when it comes to analysing whole business data sets, we need to adopt a very different way of structuring the data. And these new structures need to be simple to allow non-experts without help to be able to summarise huge volumes of data, including old as well as current data, so they can see the trends in their businesses. So, for today's class, the key words are going to be a different way of structuring that data. So let's present a very simple data structure. Data could be presented to managers as a series of rows and columns on a single sheet of paper. In the example shown, we're listing branches and products. You can see that the Sheffield branch sold £83 worth of sweets, and the Leeds branch sold £27 worth of crisps. This presentation is easy to understand, but very limited in what it can show. So let's test how easy this structure is by trying to answer the following questions. According to the data on the screen, answer now: how many pounds of fruit was sold in Sheffield? We think the answer is 53. Which city sold more crisps than Leeds? The answer to that question was London, and we chose that question specifically to show that this involved a comparison between one city and then scanning all the other cities for crisps and finding the largest. And finally, which city bought fewest drinks? The answer to that question was Cardiff, and again we make the point that this question was answered by scanning a whole row of data and then selecting the appropriate value. So, although they are very simple questions, actually finding the answer does involve a little bit of processing. In the previous slide, the data sheet was for just one day, but now let's add a second sheet for the next day's sales, and a third sheet, and a fourth sheet. We have shown only 4 pages, but of course, over time, there could be hundreds more. This is still an intuitively easy format for the end user to understand. These 3-dimensional objects are often called cubes for obvious reasons, but later in the module you'll see that inside the data structures you can actually have any number of dimensions. So let's examine how the cube structure works. You can see that drinks is going to be the frontmost row on all of the sheets. And then the city of Sheffield is going to be the leftmost column on every sheet. And in this cube, the top sheet is going to be for the oldest day. Finally, we can look at individual entries. Position of any number within the cube determines which product, which branch, and which date that figure belongs to. There's more detail about this in the next few slides. Let's see another example of this. The value 36 that we highlight here is in a fixed position. It says that drinks were sold in Sheffield on the 2nd of January. And now another. The 51 here shows that £51 of drinks were sold in London on the 4th of January. There is a key point about each of these numbers. All these different values within the cells of any one cube represent the same measure. In the current cube, each figure represents the total value of sales of a particular product in a given city on the date specified. It is never ambiguous what a number represents. So, 2 questions for you. Because it might take you a moment to find the answers, pause the video immediately after hearing the question don't let the video run on until you've found the answer. Firstly, which city sold £17 of drink on a particular date, and what date was this? The answer to this question was Cardiff. And the second question, on what date was £37 worth of drinks sold in Leeds? And the answer is the 4th of January. Can you see how you are using the rows, columns and levels of the cube? Let's try another test of your ability to read cubes. In this cube, the sales value for sweets in Sheffield on the 1st of January can be seen in the furthest away row, left column on the top sheet. You may be able to see that that value is 83. Where would you find the sales value of sweets in Sheffield on the 2nd of January? Because of the layers of the cube, you won't be able to see the exact position. If necessary, pause the video now so you can work out where the answer should be. Here are 2 more questions. Please pause the video and work out their answers. And here are some answers. In the previous slide, we asked you in which cell should you look for the value of sales in London of fruit on the 3rd of January. The way to find this is to look at the 4th cell across, the 2nd cell going from front to back, and the 3rd cell down. Do you see how that corresponds to London, fruit, and 3rd of January? And then the second question, we asked you to look up the value and also to look up which product, city and date is associated with the 2nd member of branches, the 4th member of products and the 1st member of dates. The answer to that is 67, because this is Leeds, sweets and the 1st of January. By the way, a cube is a cube is a cube. It doesn't matter which way up it is. Earlier, we talked about the top sheet representing the earliest dates and dates going downwards. But if the cube is turned or pivoted to be upside down, then the bottom sheet will be representing the earliest and the dates will go upwards. You can pivot the cube sideways as well. You can pivot in any rotation. You could position the cube so that the dates appear to be at the front. But still, £27 of crisps will be sold on the 1st of January in Leeds. Turning the cube makes no difference to this. At this point, some people find it helpful to think about how a Rubik's Cube might be rotated. Can you imagine that each little segment of the cube holds a number? Then, a particular row of segments in a direction can represent a row of values of our data. But the same row could be turned to make a column. Or again, the same row could be turned to make a depth. So, rotating the whole cube can help highlight different dimensions, but the data itself remains intact. But do not take the analogy with the Rubik's Cubes too far, because with Rubik's Cubes you twist and turn layers to move segments around. We are going to ask you to explain to yourself why you would never shuffle a layer of a data cube around. This is quite an important question, so pause the video and convince yourself of the answer before resuming. Pause the video now. Okay, we hope you found it easy to answer why you would never take one layer of a cube and shuffle it to somewhere else. But if not, think about how would you ever find a sales value for Leeds, for crisps, for the 2nd of January, if that particular cell could be rotated at any time to any position in the cube. We repeat our central point that you need to understand the X, Y, Z position of every cell fully determines which member of each dimension that cell particularly refers to. So just before we finish, let's look at the correct terminology to be using for cubes. A cube is a data structure that has dimensions, such as branches, products and dates, and it has measures. Those are the numbers inside the cells or intersections. Looking now at the dimensions, each dimension will have members. For example, Sheffield, Leeds, London and Liverpool are members of the branches. Each member will have attributes, such as the name of the member, and there can be many other descriptors too. We'll see quite a few of these in the next class. And finally, the measures, or the insides of the cube. These will always be numeric, in contrast to the dimensions, which are quite likely to be text descriptors. Finally, this is a quick way to work out what the difference is between a dimension and a measure. Dimension members very often going to provide the labels of the columns of the graphs. So for example, Sheffield, Cardiff, London, Leeds are the labels of the graph, whereas the measures, those are the numeric things, they're going to provide the height of the bars of the graph. How many things were sold in Sheffield? How many things were sold in Cardiff? How many things in London? How many things in Leeds? So the distinction between something being numeric and something being text is important. In your next class, we will lead you through using the SQL Server to develop a small cube, and you will implement various dimensions and measures yourself. We look forward to seeing you at the next class.